Hello everyone, welcome to the next session on ANSYS Workbench tutorials. In this session, we are going to analyze the drill bit for transient thermal analysis. We have already done the steady state analysis of the drill bit. Today we are going to look into the transient thermal analysis. If you recollect, in steady state thermal, we have given only one temperature, that is 250 degrees Celsius, which is the maximum temperature of one end of the drill bit. But today we are going to vary the temperature with respect to time, and we will see what is the effect on the drill bit. Transient thermal itself means that temperature will vary with respect to time. So we will start by double clicking on transient thermal. We will first go to engineering data sources, general materials. I'll use stainless steel as one of the material, and I'm going to add one more material, that is carbon steel. The value of isotropic thermal conductivity for carbon steel is 52 watt per meter Kelvin. Next I'll go to project and update project. Next I'll go to geometry and right click. Import geometry. I'll import the geometry of the drill bit. I'll give you the link for the model so that you can download and analyze. Next I'll go to model and double click on it. I'll first go to geometry and change the material to stainless steel. Next I'll go to mesh and change the sizing to fine and update. Next I'll go to analysis settings. I'll change number of steps to 10. Current step number I'll leave it to 1, and step end time I'll leave it to 1 second. Auto time stepping is your program control. I will change it to on. Now you can see these options have opened up. So I'll give initial time step as 0.1 second. I'll give the minimum time step as 0.1 second, and the maximum time step is 0.1 second. You can leave it to what it was. It will only result in more number of readings, and that is fair enough. I have just changed it to 0.1 second. Next I'll go to transient thermal and insert temperature at the tip of the drill bit. Apply. I will change the last temperature to 250 degrees Celsius, which is the highest value. You can see the starting temperature is 22, and this is repeating again. So I just change this to say 32. Now this also changes, so I'll just make it 22 back again. That is the ambient temperature. So this is the variation of temperature now over the body with respect to time. You can see here the time is changing from 0 to 10 seconds. Now over the rest of the body, I am going to insert convection. So I'll go to transient thermal and right click, insert convection. I click on apply, and fill the coefficient. I am going to click on import temperature dependent. I'll select stagnant air horizontal cylinder. Okay. Next I'll go to solution and insert thermal temperature. I'll also insert total heat flux, and I want to see the directional heat flux along the z axis. So I'll change the axis to z. Then I'll go to solution and solve. We'll first see the temperature change over the body. If you want, you can change this to no wireframe such that you can see the temperature change. Also, you can choose smooth contour over the body such that you can see a color change that is happening here. You can animate and see the result. Now you can see here there are two temperatures obtained. One is the minimum temperature and one is the maximum temperature. I will just unhighlighting the minimum temperature such that I can see the variation of the maximum temperature over the body. You can see with respect to time, with a step of 0.1 second, there is variation of temperature. It is varying from 22 to 250 degrees Celsius that we have given as the input value. If you want to save these temperatures, you can just right click, export, and you can save this as a data file. It will be a .txt file obtained. Next is the total heat flux over the body. You can see here the maximum value is 1.5 watt per mm square, and this is the variation as you can see in the color green over the body. You can animate and see the result, and you can export and save the value as I have just shown you. This is not a linear curve. If you observe, there is a variation and this doesn't look like a straight line. For a certain duration, it may look like a straight line, but over here you can see that clearly this has become a non-linear curve. Next, we can see the directional heat flux along the z-axis. Now here if you see, we will select the minimum value as it is varying and the maximum is almost the same. So I just click on the maximum one and I can see the minimum directional heat flux. It is showing along the negative z-axis, hence you are getting all the negative values. So that is how you can see a variation. You can also animate and see the result over the body. So this is with respect to stainless steel as a material. Now I'll change the material to carbon steel, which I have chosen. I'll go to solution and solve once again. For the first material that I have used, you can see the maximum elapsed time was 32 seconds. But for the second one, you can see that it is taking a little longer time. So you can see finally it has taken 4 minutes 23 seconds to get me the result. Now when I go to the temperature, I can see that this is a variation of temperature over the body. Minimum temperature is 145.45 degrees Celsius and the maximum is 250 over this body. And this is the variation of temperature. If you untick the red one, you will see the results of the right one and vice versa. Here there is variation of temperature in minimum and maximum, both of them. So you should consider both the results while analyzing. You can animate and see the result. Next is the total heat flux over the body. The red one is showing a straight line, so I just remove it and I'll see the green result. This is showing a variation of heat flux over the body. The heat flux is 0.29 watt per mm square. So you can see here this is a variation of temperature. As compared to stainless steel, carbon steel has shown quite a variation if you observe carefully. And this is the directional heat flux over the body. You can just click on the green one. Again, it's a straight line. So I just want to see the results of the red one. And if you animate, you can see the result. and the directional heat flux value is 0.00018 watt per mm square. Now, the reason for this is the value of thermal conductivity. So, let's just go back to engineering data. For carbon steel, the value of thermal conductivity we have given as 52 watt per meter Kelvin. Let's check for stainless steel. The value is 15.1. Now, this unit can be changed to watt per meter Kelvin or watt per meter degree Celsius. It will not make a difference. But if you observe carefully, the value is quite less for stainless steel as compared to carbon steel, which means carbon steel has conducted more heat from one end to the other end. Now, if you want to have a material which is conducting more heat, then you should go for carbon steel. And suppose if you want to go for an application where you do not want to conduct more heat to this end, then you should go for stainless steel. You can add many other materials which are available in the market for the drill bit, and you can analyze this for obtaining various other results. So with this, I end the session. I hope you understood the analysis. If you have any doubts, please write to me in the comment section. Don't forget to like, share and subscribe to the channel. Hit the bell icon for latest video updates. See you in the next session. Thank you.